Here we've got example 4 from lecture 8. We've got a utility function for a consumer for two variables, x and y. We've got a budget constraint. This time we're looking at the budget constraint in terms of general prices, P1 and P2, and the budget is M. What we'll find when we solve for the values of x and y that maximise utility is that these equations are the consumer's demand functions for good x and good y. First, we form the Lagrangian. So that's equal to the objective function, which is x plus 2y plus x times y. Then we subtract lambda times our constraint. So it'll be x p1 plus y p2 minus our budget m. First thing we do is find our first derivatives and set them equal to 0. So that's our first order conditions. I have first derivative of the Lagrangian with respect to x. So that will be equal to, will be 1 plus 2y, that's equal to 0. We'll leave that out. Plus first derivative of xy will just be y minus lambda time. Well, we've got an x there, so that disappears. The first derivative is 1 there. So it'll be lambda p1. And y p2 and m are constants, so they're equal to 0. So that one equal to 0. First derivative with respect to y then will be 2 plus x minus lambda p2 equals 0. Our third equation is the constraint, x p1 plus y p2 is equal to m. We can number these 1, 2, and 3. From equation 1, we find that lambda is equal to 1 plus y on p1. So just rearranging that. From equation 2, we find that lambda is equal to 2 plus x on p2. Well, they're equal, of course, because they're both equal to lambda. And so this implies that 1 plus y on p1 is equal to 2 plus x on p2. Rearranging that, find that y is equal to p1 on p2 times 2 plus x minus 1. Call that equation 4. So then we can substitute for y in equation 3, because we've got a value for y now. Equation 1 was x p1 plus y p2 is equal to m. Substituting in for y there, we'll have x p1 plus, well, we had p1 on p2 times 2 plus x minus 1 times p2 is equal to m. What we're going to do is solve for x then. Well, we can expand that out, so we'll have x p1. Well, this p2 cancels out the p2 there in the first term, so we'll have plus p1, well, 2p1 plus p1x, and then minus p2 equals m. So that's 2x p1, collecting those like terms there, plus 2p1 minus p2 equals m. So collecting the terms for x on the left-hand side and the constants on the right-hand side, we'll have 2x p1 is equal to m plus p2 minus 2p1. Dividing through by 2p1, we'll have x is equal to, well, looking at those first terms first, m plus p2 on 2p1 minus, well, 2p1 divided by 2p1 is equal to 1. There we go. So then we have, we'll call that x star because that's our maximizing value we have an expression for x now. We can substitute for x in 3. So substituting in there for x, we'll have m plus p2 on 2p1 minus 1 times p1 plus y p2 is equal to m. Well, that's 1/2 m plus p2 minus p1 plus y p2 equals m. Collecting all the constant values over on the right hand side, we'll have y p2 is equal to a half m, subtracting a half there away, plus p1 minus a half p2, divide through by p2, we'll have y star is equal to m on 2p2 plus p1 on p2 minus a half. So these two equations, this one and this one, tell us the quantity of x demanded for the prices as they vary, P1 and P2, for a given budget M.